Thank you all for joining me today for this webinar. The focus of this discussion will be about how we, as software developers, have the ability to write safe and secure code. And also, of course, the ability to write horribly bad, bug-filled catastrophes. But even if we write the cleanest code out there for a specific application, there is still the potential that an attacker can exploit an oversight in our testing and logic. Traditionally, we have turned to unit testing, dynamic analysis, such as test coverage, and peer reviews to help avoid potential risks. But this only allows us to cover the potential holes we have planned for. We, as humans, make many assumptions based on the knowledge of the design of an application, which can cloud our ability to perceive all possible threats. In order to articulate solutions for potential risks, we first need to understand the problem or the problems that exist in our development of an application. But first, let's discuss what our threat vectors are. In this webinar, we are not talking about this type of attacker. The media likes to portray hackers as these hooded creatures that only live in the dark and feed off the light of their laptop screens. And although we understand how far off this picture is to reality, it does make a point for us. Most high-profile hacks that we know about typically are about social engineering or come from convenience. The minute we as software developers make it slightly difficult for an attacker to get into our system, they will likely move on to easier targets. For example, most botnets that we know about exploited the fact that the remote login credentials for the system were still using default values. These devices included routers, IP cameras, and other internet-connected devices. The botnet creator would not have tried to exploit some tiny hole in order to get into that router you bought and haven't changed the password in 8 years. To the attacker, that's not worth the effort. So if the hooded figure is not our biggest threat, then who is? We are. We, the developers, will be accidentally, at least I hope it's accidental, writing in bugs and holes. We will accidentally be forgetting to test specific edge cases of our user input or interactions. We will be peer reviewing some code and sign off despite the fact that it will accidentally leave a big gaping hole for an attacker to gain access to our client's confidential data. Whoops. The vulnerability exists between the developer's chair and the developer's keyboard. Luckily, many of these holes are caught by white hats who will tell us about the issues they find so that we can patch it before anyone has the chance to exploit it. So as long as we get really lucky, and this is what happens every time, maybe at some point we will have a secure and functioning system. Then we can allow the attackers to come at us. Unfortunately, that's not how it works, and we must be able to detect issues before we release. So let's recap the problem. Human developers write code with bugs that aren't caught by testing or peer review. So how do we avoid writing vulnerabilities? We can start by defining 3 categories where we can improve our development workflow. Category 1. We can subset the language we are developing with to avoid using constructs that might lead to an oversight or bug. We can demonstrate this concept by discussing the Heartbleed vulnerability that was detected in the popular OpenSSL library in 2014. The library, primarily written in C, contained a chunk of code that implemented the heartbeat of the TLS SSL protocol. During the heartbeat request, an attacker could alter the packet being sent to create a buffer overflow on the target. Using a subset of the C programming language can help to avoid issues such as this by forcing developers to check the boundaries of arrays before accessing them. Category 2. We can also enforce broader coding standards on our application in order to avoid errors that fall into the category of bad programming practice. We can use the C programming language again to give an example of where a coding standard may avoid a potential issue. If we say in our coding standard that we do not want to allow assignments in expressions, this would avoid the issue where we accidentally use the assignment operator rather than the equality operator during the evaluation of an expression. Another C example is the dangling else problem. C allows us to not use brackets in an if-else block if the statement is only a single line. This can lead to an issue where the else inside of an if statement can be parsed as either part of the if directly above it or the enclosing if. By using brackets, we can avoid this kind of ambiguity. The first two categories are really things we can do while we are developing to make this last point easier. We can use advanced static analysis techniques to automate checking our code for potential errors. You might say, yeah, but that's what the peer review and testing is for. And you are correct. Peer review and testing are still an important part of the software QA process. However, they're not going to catch everything. By performing advanced static analysis, it helps us gain a deeper understanding about the consequences of each section of our code and how it will affect the overall system. And it also allows us to catch potential corner cases that we didn't think to test for. So after we finish with the advanced static analysis, the testing, and the peer review, we can have pretty good confidence that our software is bulletproof. Now that we know what to do, let's discuss in more detail why we should do it. We're going to focus on why these steps matter to us and how they will help us later in the QA process. First, why subset? As we discussed during the last slide, subsetting the language is a process of removing parts of the language which have unsafe or poorly defined features. Don't worry, you don't have to determine what those language features are. With most languages, and specifically the ones we will go into detail about later, C and Ada, the language subsets have been defined for us by language experts. A benefit of doing this that we haven't discussed yet is that subsetting allows static analysis tools to be more accurate. Let's look at an example to understand why. In the C programming language, what happens when you overflow an integer? The correct answer is it's undefined behavior of the language. Compilers can handle this in two ways: define some behavior for this operation, or just assume it will never happen. So how would a static analysis tool that is agnostic to the compiler understand how to analyze an integer overflow if it doesn't know what to expect when it happens? Let's take the same example by applying it to Ada. What happens when we overflow an integer type in Ada? The compiler will generate a runtime check exception. The static analysis tool can use this runtime check as part of its analysis to give it an accurate view of when there could be an integer overflow situation. So subsetting is important so that we give our static analysis tools the ability to analyze our code in an accurate way. This also works for human reviewers as well. If we remove undefined behavior during a peer review, you won't have to have an argument that eventually leads to a lengthy reading of the language reference manual, which makes everyone even more confused. As we discussed previously, subsetting also removes dangerous constructs from our code. If we don't use them, we can't abuse them. Again, this also helps out the software reviewer. The fewer strange things they have to look at means the more they can focus on the actual software requirements. In reality, subsetting the language is a coding standard. If anyone is not familiar with what coding standards are, they are the rules and guidelines that an organization or team has defined as things that developers should or shouldn't do. Some examples might be, thou shall use spaces, not tabs, or thou shall use meaningful variable names, or things like that. Typically, coding standards allow for code maintainability. The more standard everyone's code is, the easier it is for any developer on the team to jump in and start working. And again, this makes things easier for reviewers. We can also limit unsafe coding practices, as I mentioned before. And many times we can use automated tools to check for specific coding standard rules. And lastly, why use static analysis? Well, the promise of static analysis is that it will find bugs in our code, which basically means we are getting an automated code review that we can run whenever we want. And ideally, this code review should be more accurate than a human code review. However, the reality of the situation is not quite as optimistic. The effectiveness of static analysis is going to be dependent on many factors, including the language that is chosen, as well as the features of the language that are used. For example, it is difficult in many languages to convey the intent of a piece of code to an automated tool. We as humans know what constraints are put on a portion of the code based on how it will be used, but the tool might not know that. So the tool could provide us with garbage results that we will spend more time sifting through than is worth it. So our next question is, how do we make static analysis more accurate and useful to our application? To answer that question, we first must understand what should we expect from static analysis tools. To do that, we need to discuss the difference between sound and unsound static analysis. A sound analyzer is correct with respect to a class of defects it can detect in a complete and exhaustive way. This means that it guarantees it will detect places where a specific defect or vulnerability exists in your code. This sounds great. Why aren't we always just doing that? The catch is that because sound analyzers are guaranteed to be exhaustive, it means that there's a good chance it will give you plenty of false positives or warnings on code where there isn't actually a problem. Sifting through the results of an analysis to filter true findings from false positives can be a full-time job in itself. So sometimes the benefit of doing static analysis are outweighed by the lack of precision in the results. So let's explore unsound static analysis tools. Unsound tools typically are less accurate in their results, meaning that they might miss potential errors. But they can be more precise, meaning that the results that the tool gives you correspond to true issues rather than false positives. This makes unsound tools easier to use in everyday development. So it seems that we would have to choose between accurate but imprecise results, or sound static analysis with false positives, and inaccurate and precise, or unsound static analysis with errors missed. As dramatic as I'm making this sound, those aren't our only options. To help make static analysis more accurate and useful for our application, we need to start to think about which language and language features we choose and why. As mentioned earlier, certain language features can make static analysis more or less accurate. And certain languages can provide us with syntax that we can use to inform the analyzer about the context of our code. Let's define what we are looking for in a language and its features in order to determine which is best for us for a static analyzer. First, we want to look at syntax, or the textual representation of the program. We are interested in whether the syntax is easy to read and maintain, and what the language provides us in terms of constructs and functionality. Languages which have too low-level constructs may cause static analyzers to have a hard time understanding intent, but languages with constructs that are abstracted too far may restrict our ability to get things done in an efficient way. Next, we want to consider the type system of the language. This is usually not considered at all when selecting a language because many languages have weak typing. What this means is that the developer will only develop on top of basic system types, such as integers or floats. Whereas in some languages, we have the ability to define user-defined types with specific ranges and properties. The reason this is interesting is that as we define stricter types, it gives the static analyzer more information about the data that should live in that type. We are able to provide context to otherwise anonymous data. We have already discussed subsetting a bit, mainly that it will help an analyzer be more precise. Something we haven't considered yet is what subset will we use? Will we define our own subset? or should we rely on a subset that already exists? The answer to this question is that we want to consider subsets that already exist and can be checked by an automated tool. It would add more work to the reviewer to ensure that a language subset is followed, and we are trying to accomplish the opposite, relieving work from the reviewer by using static analysis. And lastly, we want to consider something called runtime verification, where what runtime checks are inserted by the language that can be leveraged by the analyzer. Earlier, I mentioned that with languages with strict type systems, a user can define appropriate ranges for specific types. These ranges manifest as runtime checks that are inserted anytime a variable of that type is modified. So let's say we have a type that we will call velocity, and it has a range of 0 to 200. When a piece of data is about to be stored in a variable of type velocity, the value of that data will be checked to make sure that the data is in the correct range, or 0 to 200. The static analyzer can use this information to understand what possible values that variable could have at that place in the code, and tell us if there's a potential that we might store a value out of range. For the purpose of this webinar, we are going to consider the following two language subsets, as they fulfill all of the criteria we established earlier. Most of us are familiar with the C programming language, and based on the examples provided earlier, we can see that it has some syntactic or semantic traps that make it easy to write incorrect code. MISRA C is a best practices subset of the C programming language that was intended to be used in safety-related applications. MISRA C specifies over 100 rules that are meant to help the developer avoid those traps. We are going to compare C and MISRA C to Ada and Spark. For those not familiar with the Ada programming language, it is similar to C in that it is a compiled language suitable for desktop or embedded applications. Ada differs from C in that it provides developers with higher level constructs that the developer can use to avoid common traps. For instance, in many Ada applications, pointers are not needed to complete tasks, whereas in C, they are essential to the language. The high-level constructs in Ada are the reason why it is traditionally used in safety-critical applications such as aerospace and railway. Like MISRA C is a subset of C, Spark is a subset of Ada. Spark removes certain features of the Ada language that are difficult to analyze, such as pointers and exceptions. These and other restrictions guarantee the absence of implementation-dependent semantics and prevent unspecified behavior, such as reading a value from an uninitialized variable. Although Spark is a subset of Ada, it includes all major features of the language, such as generics, or templates for all you C++ fans out there, object-oriented programming, and concurrency features. Now that we have defined our competitors, let's compare them for syntax, typing, subsets, and runtime verification features. Syntax shouldn't matter to us so much as developers, but it does contribute a significant amount to how we think about programming. And there are languages which have better syntactical designs than others. There are competitions out there where competitors try to push the limits of legal syntax by creating incredibly complex, obfuscated code. Fun as that is, it's not so great for our normal development process. We want clean and readable code that we're able to maintain for years to come. So we want a syntax that encourages clean and simple concepts. The C language encourages developers to use the preprocessor heavily for various trivial tasks. And although it is fine in some cases, those tasks can get pretty complex and require debugging. The problem we run into is that macros are not subprograms. We cannot set a breakpoint in a macro. So macros become hard to debug. We can make our programs more complex by also introducing the #ifdef concept to compile in and out sections of our code. For a developer, it becomes difficult to understand what is actually being compiled into the application. In Ada and Spark, you can still use a preprocessor, but is not required. The thing you want to do with a preprocessor can be accomplished another way. Macros can be replaced by expression functions, which are essentially inline subprograms, and if-defs can be refactored into project-level constructs, making it easier for developers to understand what they are working with. Another common syntactic problem comes up with the ordering of parameters in a function call. We have all accidentally done this where we put the parameters in the wrong order and had to debug why our program wasn't working. This problem has a name: positional parameter passing, or parameters passed based on the order they are provided. In Ada and Spark, this problem can be avoided by using named parameter passing. This allows us to say that our actual parameter corresponds to a specific formal parameter of the subprogram call. Speaking of parameter passing, in C we have two options: pass by copy or pass by pointer. If we are passing by copy, we know that the parameter is an input to the subprogram. If we are passing by pointer, is it an input? Is it an output? Is it an input and an output? Someone really should have written a comment to document what this function should do. In Ada and Spark, this problem can be avoided. Formal parameters of a subprogram have to be specified with a mode. That means to say that the parameter is an in, an out, or an in-out parameter. The compiler and static analysis tools can then check to make sure that I can't do silly things, like modify an input parameter, or forget to assign to an output parameter, or try to use an output parameter before assigning a value to it. Ada can also pass parameters by reference, like C++, and the compiler is smart enough to determine which is more efficient, to pass by copy or pass by reference. This means the developer doesn't have to worry about it. And just in case the code is refactored and the type of variable changes and suddenly pass by reference is more efficient than pass by copy or vice versa, the developer doesn't have to remember to also refactor the code to account for this. The compiler has it covered. I remember a colleague of mine once asked me to help debug some C code that they were working on. They couldn't figure out why something wasn't working properly. So I sat down and started looking through the source and realized they had variables with the same names declared. The only difference between the names was that one had a capital letter where the other didn't. They had accidentally initialized one and read the other in a function, causing this issue. It took forever to figure that out because it was such a subtle difference. And C lets you get away with this because it's a case-sensitive language. Ada and Spark are not case-sensitive, specifically to avoid the problem that I ran into with my colleague. Another big reason why I did have that issue was that we were using C-style namespacing. This is a polite way to say that the variable name was quite long in order to associate it with a specific submodule and subprogram of the code. In Ada, there is a namespacing system more like what you would see in C++ and Java, making local variables names shorter and easier to use. This contributes significantly to the readability of the source. Next, we will look at the type systems of MISRA C and Spark. The primary functions of the type system is to allow the programmer to model the data that is flowing around the program. The main difference between the MISRA C and Spark Ada type system is how closely the developer can actually model data. Since MISRA C is a subset of C, it still deals mostly with primitive system types such as integers and floats. There is no way with C to insert, let's say, a specific range on a type. Earlier, I used the example of the type velocity that went from 0 to 200. In Ada and Spark, this is easy to represent, while in C, we would have to remember to put checks everywhere in the source to check validity. Another big difference in the type system of MISRA C and Spark can be seen with arrays. In C, an array is modeled as a piece of memory with a pointer to the head. There is no information in the type that corresponds to the actual bounds of the array. If the developer wants to pass an array to a function, they will have to pass a pointer to the array and the length as two separate parameters. In Spark and Ada, the array type contains bounds information. This can be checked by the compiler and by static analysis tools. A typical security vulnerability, which I'm sure we've all heard about by now, is called a buffer overflow. This is the type of vulnerability that was at the heart of the Heartbleed issue mentioned earlier. C has no protection for this. MISRA C adds rules to check for an array access out of bounds, but most MISRA C checkers are unsound with their detection. That means that a MISRA C checker will not necessarily find all locations where this could happen. Because Ada and Spark use a higher level construct to model an array, the static analyzer can soundly check for potential buffer overflows. What we are interested in about the subsets is whether or not using the subset makes our life hard while developing. Specifically, can the subset be checked by an automatic tool? How well does the subset remove dangerous things? How restrictive is the subset? And does the subset contribute to the effectiveness of static analysis? Both the Spark and MISRA C subsets can be checked by automatic tools. However, for MISRA C there is a catch. The checker can only check a subset of the subset. Any rule in the MISRA C standard which is marked undecidable means that an automatic tool cannot completely verify whether such a rule is obeyed by the developer without issuing many false alarms. This means that it will require extra checking during the peer review to make sure everything is within the full MISRA C guidelines. Furthermore, the MISRA C standard doesn't do much to eliminate many of C's dangerous features. Because of the design of the C language, the dangerous features are intrinsic to the C semantics. For example, pointers, which are a large source of errors and vulnerabilities, are still included. The use of gotos are discouraged, but not fully excluded, and side effects and expressions are excluded, but this is one of the rules that MISRA C checkers can't fully verify. What is a side effect in an expression? A side effect means that a function will modify something outside of its local state before returning a value. Why is this bad? When a function has a side effect, it means that the order that an expression is evaluated matters. Let's look at an example to see this problem in action. Let's say we have two functions, f1 and f2. Both functions take a pointer to an integer. In f1, we are incrementing the value pointed to by the integer and returning the value at the pointer plus 5. In the second function, we are just returning the value pointed to by the pointer. We are going to use a variable a and assign it to the value of 1. We'll use the address of a as the parameter to each function. Now let's add f1 to f2 and assign that to our variable b. Let's also add f2 to f1 and assign that to our variable c. What do you think we should expect in variable b after the assignment? Let's start with f1. The value at variable p will have a value of 1 when we enter the function. We are incrementing that to 2 and then returning 2 plus 5, which should be 7. Let's now look at f2. We are returning the value pointed to by p, which we have just incremented from 1 to 2. So our return is 2. The value we have in variable b should be 9. Let's now do the opposite, adding f2 to f1. We are going to reset a to 1. Then we call f2, which will return the value pointed to by the address of a, which is the value in a, or 1. Next, we call f1. The value pointed to by p is at 1, so we increment it and return 2 plus 5. So we return the value of 7. So what value do we now have in variable c? 1 plus 7 equals 8. Wait, that's different than last time. Based on our knowledge of math, the order we add things shouldn't actually matter. So what did we do in this program that meant that the order we are evaluating things matters? Side effects. function f1 has a side effect, meaning that we are modifying a value outside of the local scope of the function before the function returns. This is a big issue with using pointers in C. It is difficult to avoid side effects. In Spark and Ada, this problem can be avoided by using in-out or out parameters to return values from subprograms. Ada in Spark also distinguishes between procedures, which do not return a value, and functions, which do return a value to their callers. When using Spark, the difference between functions and procedures becomes very obvious. Spark does not allow side effects in functions, meaning you can't use a function and modify anything outside of the local scope. This manifests in code as a function with an in-out or out parameter. Instead, you can use a procedure. For the developer, it's easy to see now that if there's a function in some Spark code, it's computing an expression or crunching some data rather than modifying something in the global scope. And the Spark tool can soundly check for this, making the life of the peer reviewer much easier. The last piece of our comparison that we want to consider is what runtime verification we have. Meaning, do we have the ability to detect runtime errors in the code statically? Ideally, we would want to be able to prove that our program is completely free of runtime errors. With both Spark and MISRA C, static analysis can detect certain types of runtime errors, such as integer overflows and divide by zero. Since MISRA C has many undecidable rules, it's difficult to get to a state where you can guarantee complete absence of runtime errors in your program. Because of the design choices made in Spark to favor static analysis, we can actually do a sound static analysis of the same undecidable rules in Spark, meaning we can get complete absence of runtime errors, and actually using a feature called contracts, we can go even further to guarantee certain safety or security properties of our code. This is an interesting concept because although runtime errors can be a large source of vulnerabilities in an application, it is easier to exploit poorly implemented sections of code. For example, let's discuss a situation where we can have a possible SQL injection. Say we have a subprogram where we take an input and generate an SQL query to send to a database. Our first thought is the input trusted, or do we need to sanitize it? If we need to sanitize it, what are the requirements? And how do we make sure our implementation meets all of our requirements? Our usual answer to this question is to make sure that we do comprehensive testing of the subprogram. However, with contracts, we can manifest our requirements and design into pre- and post conditions, which are basically assertions that are checked at the entry and exit of a subprogram. These contracts can be used by static analysis tools to gain an understanding of what you're trying to accomplish in your subprogram, and using that information can determine if the subprogram is being used correctly and if it was implemented correctly. So ideally, we could reduce our amount of testing on this piece of code because our static analysis tool will give us confidence that our implementation follows our design requirements. Contracts are really the most powerful tool we have in our arsenal to make sure that our code is correct and free from exploitable defects. It provides extra information to our static analysis tool so that it can understand what our intent is. And with this, it becomes another peer reviewer rather than a pain in the neck tool that we spend too much time trying to get valid information from. Now that we have established how we can write better, safer, and more secure code, and how we can verify that it is indeed safe and secure using a static analysis tool, let's discuss what type of issues we can mitigate. In these slides, we will use the common weakness enumeration mapping that was created by the MITRE Corporation to discuss potential vulnerabilities that we may have in our code. These CWEs are a catalog of common issues or weaknesses that are found in source code. They provide a common language that developers can use while discussing with security professionals when developers are asked about potential risks they may have in their code bases. Using the Ada programming language, we already gain significant confidence in the security of our code based on the types of issues that are mitigated just by the language. Since the Ada compiler manifests many of these checks into runtime exceptions, we can literally catch potential issues by monitoring exceptions in our application. Earlier, we discussed how buffer overflows work. In Ada, if you try to index into an array with an index that is outside the bounds of that array, an exception will occur. These types of runtime checks means that it is harder for an attacker to exploit runtime code. However, these runtime checks do come at a cost. Since the compiler is inserting extra code into the application, it is possible that the final binary will be slightly larger than expected, and the performance of the application could suffer because of the extra checks being executed. So many times, development teams will want to keep these runtime checks in the code only for testing purposes, and ship the final binary with these checks turned off. In that case, the final binary has none of the guarantees that these types of issues are actually mitigated. This is where static analysis comes in handy. We are able to check for everything we saw on the last slide plus more that aren't caught at runtime using static analysis. In this case, we can ensure that our final binary doesn't contain any of these vulnerabilities. Here I have listed two static analysis solutions. CodePeer is generally used as an Unsound static analysis tool that is fit for analysis of full Ada code. As we discussed earlier, since Spark is a sound analysis solution, it requires that we subset the Ada language to the Spark subset in order to perform the static analysis. With CodePeer and Spark, we can detect everything that would manifest as a runtime check, as well as look for potential race conditions in our application. We can also guarantee that we are initializing variables before use, which is the source of potential errors and exploits. With Spark, we also have the added benefit of removing pointers, which mitigates many more potential issues. When using the CodePeer and Spark static analysis solutions, developers have the ability to map their findings to these CWEs so that they can provide reports and analysis to security teams about the potential risks that may exist in their code. So now we have the language and the tools necessary to make sure we, the developers, aren't the biggest threat to the security of our own applications. Now, how do we integrate this into our current workflow? The great thing about static analysis is that it can act like your on-demand peer reviewer, meaning you can run the tool as often as you'd like. In many cases, developers use the tool to sanity check their changes before code commits. This way, they can guarantee that any changes they made didn't introduce any glaring issues into the codebase. The developer can then show the results of the static analysis to the peer reviewer during the actual peer review as a piece of data to be reviewed. This gives the peer reviewer confidence that the codebase is free of certain types of issues. In many situations, developers will analyze a few files at their desk and then commit their code. As part of a continuous integration system, the builder might run a series of test suites on that commit. The builder can also run static analysis on the entire codebase at that commit, potentially flagging issues that are not caught by the test suite. You might also have a testing and QA team that could be running static analysis as part of the QA process. The testers can then use the information from the static analysis tool to inform the generation of future test cases and feed that back to the developers in order to make applications more secure. Ideally, you have all of these cases happening. Developers at their desk finding issues as they show up. CI systems catching issues that are potentially the interaction between two developers' changes, and QA teams using static analysis to bolster testing. Using the tool at all of these stages will increase the integrity of the application, as well as minimize the amount of time it takes for an application to clear QA and ship. During the development of your next security-critical application, make your life easy. Use Ada and Spark and utilize the CodePeer and Spark static analysis tools. You will end up with an easy-to-read, maintainable, and vulnerability-free software that you are proud to ship. Thank you so much for attending today's webinar. I hope you will all check out static analysis and how it can help you in your development process. For more information, check out the links listed on this slide. These articles go into more detail about Ada versus MISRA C and using static analysis for security-critical applications.